Okay, this is section 10.4, tree diagrams, tables, and sample spaces. You should have at least read over the book, watched some videos, done something to get familiar with this material. This is simply a worksheet. First off, tree diagrams are associated with outcomes and probabilities. In other words, if I have an experiment, for example, of tossing a coin twice, on the first toss, I can either get heads or I could get tails. On the second toss, no matter where I'm at after the first toss, I can either get heads or I can get tails. If I got tails, the same situation, heads or tails. As a result, I could either be here, that is the outcome, getting heads twice. I could be here, that's the outcome of getting heads first, then tails. I could be here, I could have gotten tails first, then heads. And then I could be here, I could get tails first and tails second. So these are the possible outcomes associated with the experiment. From looking at the outcomes, when I know all possible outcomes, I can then determine probabilities of certain events. For example, the probability I get exactly one head would be 2/4. Reason why? I have two possible ways of getting exactly one head. There are four possible things that can happen, and that is how we define probability, right? The number of ways you can do something divided by the number of ways you can do anything. Well, a tree diagram helps us visualize what those outcomes can be. Something else you should be familiar with are the terms and or. In mathematics, the word and means both. Both things occur. Both things occur. I do this and I do that. I'm saying I'm doing both of them. The word or means at least one of the two. If I go to the park or I go to the movies, I am saying I'm going to do at least one of them. It is not an exclusive or. So as we walk through this chapter, just keep in mind the meaning of and. And means both things occurred. Or means at least one of them occurred. A quick review of the meaning of probability. Probability is the likelihood that something will occur. For example, the likelihood we get tails when we toss a coin, the likelihood we get an even number if we toss a six-sided die, etc. But more formally, probability under the assumption we can count, meaning we know what the outcomes for the experiment are. It is the number of ways that something can occur divided by the number of ways anything can occur. So probability in this definition here is consisting of two counting problems. You count the number of ways it can occur. You divide it by the number of ways anything can occur. It is based upon what we know and the experiment. So probability is always based upon what we know, and it's based upon the definition of the experiment. You always have to keep in mind the experiment. Let's consider, for example, an experiment is selecting a ball from a bag, that's supposed to be a bag, containing 3 red, 2 blue, and 4 green colored balls. I would like to know the probability that we select a red. Well, to select a red, we need to know how many ways we can get a red. There are 3 ways to get a red. The denominator is the number of ways we can get anything. There are 9 balls in the bag, so there are 9 ways to get something. Notice the definition. We're counting how many ways it can occur. We're counting the number of ways anything can occur. The probability we get a red or a blue. Well, how many ways can we pick red or blue? At least one of them. Red or blue doesn't matter. Well, we got 3 red, 2 blue. There's 5 ways we can pick one of them, right? That's the numerator. Denominator, Number of ways we can pick anything, 9. Probability of selecting a red and a green. Now the word and means both, right? Both of them. Our experiment is selecting a ball. That's why you have to keep in mind the experiment. You need to know what's going on. Well, if we're selecting one ball and it has to be red and green, there are 0 ways for that to happen. So the probability of that is 0. So always keep in mind the true definition of probability in terms of counting. Always keep in mind it is really based upon what we know. We'll see that later on, really. But also keep in mind what the exact experiment is. If I was selecting 2 balls, this could occur down here. But I'm selecting a ball. Moving on. Okay, tree diagrams can help us visualize outcomes and probabilities. So we're going to build a tree diagram here. We have an experiment where we select a ball from a bag, and that bag has 1 red, 2 blue, and 1 green colored ball. Then we're going to toss a fair coin and note heads or tails. So this experiment consists of selecting a ball, then tossing a coin. We want to construct a tree diagram to determine what the sample space is and the probability of selecting a blue and tails. So you can stop the video and try this yourself. All right, so the first step in the experiment is to select a ball. I could either select a red ball, one of the blue balls, or the other blue ball, or the green ball. So those are the things that could happen on the first step of conducting the experiment. Getting the red, one of the blues, the other blue, or the green. Now once I've selected the ball, I'm going to toss the coin. No matter where I'm at, here, here, or here, or here, I either could get heads or tails. Heads or tails. Heads or tails. Heads or tails. So now the experiment's been conducted. If I end up right here, I got red with heads. Right here, red with tails. If I get here, a blue with heads, a blue with tails, a blue with heads, a blue with tails, a green with heads, a green with tails. So all of these things right here represent the possible outcomes. So this is the sample space. The sample space consists of all possible outcomes based upon the experiment. Now, what is the probability I select a blue and a tail? The probability I get blue and tails is, can I count how many ways I can get a blue and a tail? Well, blue and tail, blue and tail. There are 2 ways. Can I count how many ways I can get something? 1, 2, 3, 4, 5, 6, 7, 8. 8 ways. So 2 over 8 is 1/4 or 25%. Now notice a tree diagram obviously would not be possible if you had, for example, a bag that contained 100 different colored balls, right? Or if I was tossing the coin a gazillion times, right? It's just not possible. But again, when you can visualize something or the idea behind something, it can help you understand the more complex problems. So let's move on. So stop the video. Okay, you should be pausing the video. I'm not going to read the problem to you. I'm going to just work it out to save recording time, right? So you've read this problem over. Hopefully you have tried to work this out. And here are the questions. How many outcomes are in the sample space? So we built a tree diagram. Our experiment consisted of spinning a spinner that could get A or B, a second spinner that could get 1, 2, or 3, and then a third spinner that had a color on it, green or pink. So again, I conducted the first step of the experiment. I either went to A or B, but no matter where I'm at here, I could go to 1, 2, or 3. No matter where I'm at here, 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 or here, I could get green or pink. So here are all the possible outcomes. This is the sample space. How many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 possible outcomes. Okay? Now, how many outcomes are such that the number is selected is at least a 2? How many outcomes are such that the number selected is at least a 2? Well, let's circle them in red. At least a 2, 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 a 2, at least. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible ways of getting at least a 2. Find the probability the experiment results in getting at least a 2. Well, definition of probability, how many ways can we get something that is at least a 2? 8. How many ways can something happen? 12. You're responsible for reducing things to lowest terms or expressing something in terms of a decimal number if that is what is being asked for. Okay, so I'm going to leave it as 8 over 12, which we also know is 2/3 or 0.666666, whatever. Let's move on. You need to stop the video, read the next problem, and try it out. Okay, again, hopefully you've read over the problem, tried it, gave it some thought. All right, so we have events over here. We have the possible outcomes listed over here in the columns, and we want to check off the outcomes associated with the given event. A boy on the second birth or the third birth. So again, you read over the context of the problem. We want a boy on the second birth or on the third birth. So boy on the second or third, so either one. Or means either. That's a very important word in probability. We should be circling it. First, second or third? Second or third? Nope. Nope. Yes. 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 And yes. These are the outcomes where a boy was born either second or third. How many are there? 1, 2, 3, 4, 5, 6. So there are 6 ways for that to occur. The number of possible outcomes, 1, 2, 3, 4, 5, 6, 7, 8. So 6 over 8. Second event. Alternating girls and boys with either coming first. So boy, girl, girl, boy, alternating, right? So girl, boy, boy, not alternating, not alternating. Boy, girl, girl, not alternating, not alternating, not alternating, not alternating. Here, boy, girl, boy, right here. That's an alternating one. And this is a girl, boy, girl. That's alternating. So there are 2 ways to get alternating sexes. 8 ways for something to happen, and so that is the probability. For the last one, exactly one girl. Exactly one girl. Exactly one girl. Exactly one girl. 3 ways to get one girl. 8 ways for something to happen. That is the probability of exactly one girl. Moving on. Okay, another tree diagram type problem where a tree diagram helps us visualize the outcomes and can help us calculate the probabilities, right? So you've looked at this problem here. Basically, again, we perform the experiment and we break the experiment here up into steps. President, Vice President, Treasury selection, right? So you should be familiar with this. If you follow any one given path, it leads to an outcome. How many outcomes are there? If you count all these outcomes, you should get 12. How many outcomes are in the sample space where John or Ann is selected? John or Ann, it don't matter. Well, here's one with John. John, neither one, neither one. They have Ann here, Ann, John, John, and that's it. So these are the ones that have John or Ann. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 outcomes associated with John or Ann. Well, we want the probability that John or Ann is selected. The probability of an event is how many ways it can happen, how many ways anything can happen. Our final question is Linda and Jessica. So we need both of them. So let's go to a different color here. I'm going to go to purple here. We need Linda and Jessica to be in the outcome. So Linda and Jessica. Here's Linda and Jessica right here. Here's Linda and Jessica right here. Okay, I only see 2 of them. So there's 2 ways to get Linda and Jessica. There are 12 ways to get anything, so there's the probability. I think there's one more slide, so let's stop the video and work the last problem. Again, hopefully you have read over the problem, looked at it. We have several events going on over here. We have all possible outcomes listed up here, and we want to identify the outcomes to the events and then determine probability. So our first event, we get heads on the second toss. Heads on the second toss, second toss, second toss, second toss. Doesn't say anything else. Don't imply something that's not been implied, right? It said heads on second toss. It said nothing about the other tosses. So we have 4 outcomes where you could get heads on the second toss. Okay? There are 8 possible outcomes. 1, 2, 3, 8 possible outcomes. Tail on each of the first 2 tosses. So the first 2 has the result in tails, right? So no, 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 no. Tails first. Tails on each of the first 2 tosses, right? And this one right here. So again, we said nothing about the third toss. So we have 2 possible outcomes out of 8. More tails than heads. More tails than heads. Well, we got 2 tails here. 2 tails here. All tails here. 2 tails here. So 4 out of the 8 result in more tails than heads, right? All right, that's it. End of this particular short video on section 10.4. Thank you.